Hello, everybody. Thank you for joining the second monthly colloquium of Hel.A.S for this academic year. We are very happy and honored to have together with us Professor Georgios Magdis from Danish Space Institute and the Niels Bohr Institute of University of Copenhagen in Denmark. So Georgios graduated from the physics department of the University of Crete in 2003. Then he continued in Crete and carried out his master's in 2005. And then he moved to UK and carried out his PhD in the University of Oxford. And he completed his PhD, he got his PhD in 2008. After obtaining his PhD, he first moved to France, and particularly and specifically to Centre d'Astrophysics, Hel.A in France, as a postdoctoral researcher, where he spent 3 years from 2008 to 2011. Then he joined University of Oxford from 2011 to 2015 and worked as a research fellow. And since 2015, he is in Denmark. He first joined University of Niels Bohr Institute of University of Copenhagen in 2015 as an assistant professor and then a Carlsberg fellow. And since 2018, he is an associate professor. The research interests of Georgios are on observational cosmology and galaxy evolution. He is a worldwide expert on this field, and his research is on the study of galaxies through cosmic times, and he is looking into problems regarding the formation, growth, and evolution of galaxies, as well as the properties. The way he is tackling these very important problems is by using deep multi-wavelength cosmological surveys, giving particular emphasis in observations on either infrared or radio. For that, he used almost all major astronomical facility, either on ground or in space, including ALMA, Herschel, Spitzer, JWST, VLT, and Keck. Georgios is a co-founder of a Center of Excellence in Denmark called Cosmic Dawn of Excellence, working on problems of observational cosmology. And today's talk will feature galaxy evolution, insights, challenges, and opportunities in the golden era of multi-wavelength astrophysics. So without further delay, I'm giving the floor to Georgios. So Georgios, please go ahead.
Thank you very much, Spiro. Thank you very much for this lovely review of my last, how much this, almost 20 years. That's nice to hear from a third party. So welcome everyone, and thank you very much for joining online. Today I will talk to you about galaxy evolution, as the title says. And since I've been anticipating an audience of mixed expertise, I will first introduce some basic concepts that motivate the questions that we were trying to address. Then I will present some key results that I think have shaped a new paradigm into understanding of how galaxies evolve, how galaxies form, evolve, and eventually die. And in the end, towards the end, I will discuss with you some ongoing projects that I think are paving the way for future directions, especially in light of this impressive array of multi-wavelength astronomical facilities that are progressively becoming online. So to begin with, let me, did the slide, is it transiting? Can you see the second slide?
Yes.
Okay, perfect. All right,
yes.
So it's working. All right. So if you take a deep image of the sky with a telescope like JWST, like Hubble, you will see that the universe is filled with galaxies that come at a wide range of colors, shapes, and sizes. So the obvious question that comes to mind is, how does this baryonic structure we see today emerged from the density fluctuations of the CMB? Or to put it more simply, how the heterogeneous universe we see today emerged from an almost homogeneous beginning. Now, there are several ways to address this question, but one of them, and a very successful way of doing that, is by looking at the galaxies, which are the building blocks of the universe. So actually, galaxies resemble a lot like living organisms. They form, they grow, they evolve, and they eventually die. And these phases in galactic evolution are characterizing three main types of galaxies that you see here. First of all, we have the normal galaxies, like our Milky Way, that are peacefully converting the gas into stars. Then we have the star-bursting galaxies that you see here, that are galaxies that are forming stars at furious rates compared to their neighboring galaxies, so 10 to 100 times faster compared to the normal galaxies. And we believe that this is due to a major merger event when two galaxies collide, and you can see that in their distorted morphologies. And the third class of general categories of galaxies are the dead galaxies, the quiescent or passive galaxies, as we call them, that you can see here on the right, which were galaxies that have ceased their star formation. They are not forming any new stars. Now, if we want to understand the evolutionary path between, or the transition between these various stages in galactic life cycle, we first need to answer some basic questions. First of all, we need to measure and capture the sensors of the galaxies, so the demographic of the galaxies, and especially the very first galaxies of our universe. Then we need to understand the physics that regulates their growth, and finally try to understand when and how galaxies die. And to do that, we have to think about what are the main components of a galaxy. And I'm sure that you all know that we have the baryonic matter, which is made of stars, gas, dust, which all these are enshrouded within a dark matter halo. And there is a constant interplay between the dark matter halo and the baryonic matter that resides within the galaxies, in the sense that gas is accreted into the dark matter halos. The gas collapses to make molecular clouds. The molecular clouds then collapse to produce stars that burn the hydrogen into heavier elements that are then, through supernova or stellar winds, are brought back into the interstellar medium, which are and they form the seeds for metals and dust in the interstellar medium of galaxies. So obviously, if we want to understand galaxy evolution, we have to properly measure, understand, and characterize each one of these components. But this is not as straightforward as one might think, because as you can see on the bottom, each of these components have different observational signatures. So what you see here is the Andromeda galaxy as observed in different wavelengths, and I'm sure that you can appreciate how the structure of the shape and the overall the overall structure of the nearby Andromeda galaxy changes when observed at the different wavelengths. And of course, different wavelengths are probing different components of galaxies. So if we are to address galaxy evolution, we need to combine multi-wavelength observations and get the full picture. To appreciate that more, here is an HST image of a nearby galaxy, of a nearby merging system, the antenna galaxies, where this HST observation, high resolution HST observation, is tracing the sites of newborn stars. So what you see here in blue are the new stars that are formed in this system. Now, this is the complementary image provided by ALMA that pinpoints the position of dust and gas, which is not accessible in shorter wavelengths. So by combining these multi-wavelength observations, we are now in position to measure all the fundamental properties for this system, which are the star formation rate, the amount of stars, the amount of gas that resides in this galaxy, and therefore understand things about its history, but also make predictions about its future evolutionary path. Now, thanks to deep multi-wavelength surveys, we can play this game not for a single galaxy, but for large statistical samples. And here you see one of the deepest images from a particular part of the sky. This is, I think it's the Hubble Deep Field North, Hubble Deep Field South, and you can see the array of telescopes that have been used in order to target the same particular part of the sky. And so we can quantify these fundamental properties, not just for one galaxy, but for several galaxies, for several thousands of galaxies that reside at different redshifts. And therefore, by bringing them together, we can actually paint a picture into the cosmological evolution of this system as a function of time. One of the most important achievements of these multi-wavelength surveys has been the fact that we have managed to characterize and trace the evolution of the star formation activity of the universe. What you see here in this plot is on the y-axis is the average star formation activity. It's the of the universe within a given volume as a function of time. So from left to right, we're moving from the Big Bang to the present day. And what you actually can see here is that in the beginning, from the Big Bang, and approximately for the first 10% of the cosmic history, or 20% of the cosmic history, the universe goes, it's a period that we call a cosmic morning, where the universe forms its first stars and its first galaxies, experiencing a very rapid growth in its star formation activity. Then, and for the next 4 billion years, approximately, we're entering into the cosmic noon, where the galaxies are forming stars, where the galaxies form most of the stars that we see today, and the galaxies experience substantial growth. Then, and as we move to the present day, towards the right, the galaxies start slowly to die off. They reduce the star formation activity, and overall, the star formation activity of the universe drops by a factor of 10 from redshift 2 to the present day. That corresponds to redshift 0, entering in what we call the cosmic dusk. So we have managed to split the galaxy evolution into 3 main epochs. It's the cosmic morning, when the first galaxies and the first stars are born, the cosmic noon, where the galaxies grow, and the cosmic dusk, where the galaxies begin to die. Now, I'm sure that you will agree with me that describing is not the same as understanding. So by looking at this picture, there are several questions that need to be answered in order to understand why the universe is behaving in that way. So the obvious question is, what drives this rise, the peak, and the decline in the star formation activity in the universe? And in the process, try to understand what dictates the baryonic cycle across cosmic time, and understand how the galaxies assembled their stellar mass. In order to answer these questions, what we have been trying to do is to establish some scaling relations between the fundamental properties of the galaxies, and see how these scaling relations change as a function of time, but also as a function of galaxy type, like the three main type of galaxies that I discussed before. And one of the most intriguing and interesting insights is offered when we look at when we compare, or when we plot together the star formation rate versus the stellar mass of the galaxies. The star formation rate, you can think about it about the rate at which a galaxy is producing new stars at the moment of the observation, whereas the stellar mass, you can think about it as the integral of the past star formation history, or the integral of the past star formation activity of a galaxy. And what we see is that the majority of galaxies, approximately 9% of the galaxies at all redshifts, tend to follow a tight relation between these two quantities. Of course, outliers do exist, with the starburst galaxies that I discussed before falling above, exhibiting an enhanced star formation rate for their stellar mass compared to the average population, and the quiescent galaxies that quite naturally, since they're dead and passive, they have very low amounts of star formation or zero star formation for their stellar mass. Now, the most important thing about this main sequence of star formation, there are three important characteristics of this main sequence of star formation, as we call it. The first one is that it appears to hold out to redshift 6. So it appears to be present over the last 10 billion years and to be followed by approximately 90% of the star-forming galaxies in our cosmos. The second characteristic is that the normalization of the main sequence, or of this of the relation between the star formation and the stellar mass, seems to increase as a function of redshift, something that mirrors, if you remember, the overall increase of the star formation activity of the universe as a whole. But I think that the most important and the most intriguing characteristic of this main sequence is its small scatter, which is approximately 0.2 to 0.3 dex at all redshifts and at all stellar masses. Here I only show it at redshift 0, but the same scatter applies at a higher redshift. So what this means is that at a given cosmic time, so at a given redshift and at a given stellar mass, the star formation rate of approximately 90% of the star-forming galaxies varies only within a factor of 2, which is something that is quite impressive, because this means that there is a strong memory between the present star formation activity and the past star formation activity of the galaxy. So there is a crosstalk between what the galaxy was doing in the past with what it's doing at the moment regarding its star formation rate. And if you think about it, this means that there must be some sort of uniform, smooth, and continuous star formation history as the main avenue of galaxy growth, instead of stochastic star bursting event. Because in that case, if you have a stochastic star bursting event with that dictates your star formation rate, then the scatter between the star formation rate and the stellar mass will be much wider. However, there is only a few things that you can learn about the galaxies without bringing into the picture the gas, and in particular the molecular hydrogen, which, as you know, is the main fuel of star formation. However, unfortunately, our telescopes cannot directly detect the molecular hydrogen into typical conditions of the interstellar medium, and therefore we have to rely on indirect tracers in order to measure the amount of gas that resides within the galaxies. And over the years, we have been carrying out concerted efforts in trying to build an inventory of indirect gas mass tracers by targeting a range of atomic and molecular species, and trying to build some methods in order to measure, to weigh how much gas resides within the systems. This particular topic merits its own seminar, or if its own conference, I would say. But the bottom line that I would like to say, that the key result, one of the key results out of all these surveys that have been trying to quantify how much gas is in the galaxies, is the realization that the gas fraction, which is the baryons that are in gas over the amount of baryons that are already in stars within the galaxies, evolves as a function of redshift, and it seems to increase by a factor of 10 from the present day to redshift 2, so over the last 10 to 11 billion years, mirroring again the overall increase of the star formation activity of the universe. So it seems that the increase in the star formation activity of the universe goes hand in hand with the increase in the amount of gas that is available within the galaxies. And indeed, we find that the majority of galaxies, again, the majority, 90% of the galaxies, follow a second tight correlation, this time between the star formation rate and the molecular gas and the total amount of gas that resides within these systems. Here you see the galaxies here, color-coded by the redshift. And again, we do identify a population of outliers, of approximately 5% of these systems that are the starburst galaxies that we discussed before, that aside of having an enhanced star formation rate for their stellar mass, they also appear to have an enhanced star formation for the molecular gas. Now, for those of you who are more familiar with this picture, I should also say that the sharpness between the bimodality in the SFR, in the star formation rate molecular gas relation between normal galaxies and starburst galaxies largely depends on several assumptions of the gas phase metallicity, for example, and this is something that will be addressed in the near future. Now, if we take the ratio of these two values, so the star formation rate over the molecular gas, we have a quantity that is called the gas depletion time scale. And this quantity, if you do the units, you'll find that it has units of time, and it's telling you in how much time a galaxy will run out of gas if it keeps forming stars at the same pace as the one observed at the moment. And what we see again is that the majority of galaxies, again, over the last 10 billion years, have gas depletion time scales that has only changed by only a factor of 2 over this cosmic time span. And again, these starburst galaxies having a factor of 10 higher gas depletion time scale compared to the normal galaxies. Now, if you think about it, what this is telling us is that the average galaxy has a gas depletion time scale of 1 to 0.5 gigayears, to have a gigayear, over the last 11 billion years. And this can only happen if there is some sort of replenishment of gas. Otherwise, the galaxies would run out of gas, and we wouldn't see them to have this amount of this gas depletion time scale for such prolonged period of time. And indeed, we believe that this is one of the most direct or indirect evidence of gas inflow into the galaxies from the dark matter into the dark matter halos, something that is predicted by simulations, but unfortunately has not been yet observationally confirmed. So here you see the gas inflow from the IGM into the dark matter halo that fits the galaxy in order to make stars. Now, in this scenario, the gas accretion into the dark matter halos should be proportional to the dark matter halo, and therefore you should expect a correlation between the halo mass and the star formation rate of the galaxies. And indeed, by looking into IFU spectroscopy, some preliminary results using CMOS and H-alpha kinematics, we do find evidence that the star formation rate measured by the H-alpha line tends to correlate with the mass of the host halo of the galaxies at redshift 1, giving support to the idea that the halo, the halo mass regulates the amount of gas, and in its return, the amount of gas regulates the star formation rate of the galaxies. So these scaling relations that I just discussed, along with other lines of evidence that touch upon the interstellar medium of the galaxies, such as the temperature of the dust that is in the systems, the compactness, the radiation field, and the kinematics, when all brought together, they seem to to build a nice paradigm in galaxy evolution, where 90% of the star-forming galaxies grow along the main sequence that we discussed by converting the gas into stars in a secular, smooth, and a long-lasting mode of star formation before they run out of gas and they shoot down to quiescence. Now, a smaller fraction of 5 to 10% of star-forming galaxies, for whatever reason, we believe that it's a major event, they enhance their star formation rate. They consume their gas at a very fast pace, and then they shoot down into quiescence. And all this is orchestrated, all this is regulated by gas inflow and outflow within the dark matter halo. Now, of course, this is a evolutionary picture that has gained a lot of momentum and is currently implemented in the majority of theoretical works and simulations. However, it's by no means it can be regarded as a complete picture into the galactic life cycle or into galaxy evolution. Indeed, there is still very little that we know about the first galaxies and the first generation of quasars and the first gas and metals of the universe, the ones that are deep into our cosmic morning, into the cosmic dawn, so the first billion years of the existence of the universe. At the same time, we need, in order to get a complete picture, we need to push in detail and start digging inside the internal structure of the galaxies and trying to understand the physics that regulate their evolution and the physics of the ISM. For example, one of the major questions that still remains unanswered is what are the internal processes responsible for the death of the galaxies? And more importantly, what keeps the galaxies dead? Third, we need a push in scale and in theory, in the sense that we would like to get better and more accurate measurements of the dark matter halos of the galaxies and understand the clustering of the systems. So to put it together, we need a push in completeness and redshift and look back time. We need a push in detail and also a push in scale. And this will very soon be, and is already being possible thanks to an impressive array of instruments and telescopes that are already online, or there will soon be available to the astronomical community. Here you see posted some collection of such systems like the ALMA, the SKA, the ELT, NGVLA, and on the top, the bottom right, you see Euclid. But of course, the main protagonist here is this guy here, the JWST, that is supposed to be launched in December 18th and is promising to pierce through time and detect the first galaxies in the universe and go there where Hubble could not go. Of course, this is thanks to this 6-meter mirror, but also the fact that it's that JWST is sensitive to the near and mid infrared instead of the optical that was the primary wavelength range of Hubble. So at the moment, a few weeks ago, JWST arrived in Transguiana, where it's supposed to launch in December 18. While it was being transported there were some thankfully unfounded speculations that there will be pirates who will try to kidnap the telescope. Thankfully, this didn't happen. After its launch, that you see here on the right, the JWST will deploy its 6-meter mirror and then travel for about 3 to 4 months to the L2 point where it's going to start its observations. I was really happy to see that there is a lot of involvement in the JWST GEO, and a lot of success in the GEO proposals from Greece, from Calliope and from Tanyo. Those are the two that I identified. I'm sorry if there are more. So that's extremely encouraging and I was extremely happy to see that. Now, the point that I would like to make here you see on the y-axis, the angular resolution, and on the x-axis, the wavelength and frequency covered by the several instruments that are already available or will soon become available. And the point that I would like to emphasize here is that we are entering into the sub-arc second resolution across the electromagnetic spectrum. So we will be for the first time in a position to study all the components of galaxies, or the baryonic components of the galaxies at an unprecedented spatial and spectral resolution. So in this second part of my talk, I would like to highlight some ongoing projects and some future directions that we hope are paving the way for the full exploitations of these systems or of these facilities. And I will start with the unexpected, I would say, discovery of a population of galaxies that were lurking in the dark, that had so far been invisible. So indeed, there are patches of the sky that seems to be dark, even with the deepest and most sensitive and sharpest images taken with Hubble. But at the same position, ALMA has revealed a new population of galaxies, of dust enshrouded galaxies, of dusty star-forming galaxies in the early universe that, as I said, have been missed by the deepest optical surveys. These systems tend to reside at high redshift, and we believe that, it's the gigantic amount of gas and dust that attenuates the starlight and makes these galaxies invisible by Hubble. So it seems that in our effort to get a complete picture of the galaxy population across cosmic time, it's not only a race against cosmic time that results to the cosmological dimming that makes the galaxies fainter, but it's also a battle against cosmic dust. But for that, thankfully, we have ALMA. Here is a more detailed description of these optically dark, or HST dark sources, as we call them. Here in the yellow circle, you see, so in the background, it's the ALMA map of the at 1.1 millimeter of the good south field. This source here is a clear detection in the ALMA map that when we see the corresponding part of the sky in the H and K band, we find empty sky. So what you see here is the contours of the ALMA contours on top of empty sky, suggesting that this galaxy does not have an optical counterpart. We're carrying out a series of ALMA surveys in order to identify these systems, like the ALK survey, the Cosmos ALMA 2 millimeter survey. Those are some surveys that I'm happy to discuss with you later on. And it appears when we follow up these sources spectroscopically, it seems that indeed they reside between redshift 6 and 3. So from the epoch of reionization to the epoch of obscuration, though. So from redshift 3, so from the epoch where the universe ionizes to the epoch where the bulk of dust and metals are produced in the early cosmic times. And what it seems quite puzzling is that the abundance or the number density of these systems tends to be 2 orders of magnitude larger compared to what is expected from our simulations. What you see here in this spectrum is the most distant, to my knowledge at least, dusty star-forming galaxy that it's not lensed. which has been spectroscopically confirmed to be at 5.85 with ALMA, begging the question, of course, what are the other population of galaxies that we might have missed? Now, the high resolution offered by ALMA, when complemented with HST observations and soon with JWST, allow us to bring together the stellar, the dust, and the gas component in a fashion much like to what I showed you about the antenna galaxies at redshift 0, but this time out to redshift 2, 3, and above, which is something in my eyes that it's impressive, because we're starting to understand and study the galaxies 11 billion years ago at the level as we study the galaxies in our neighborhood. So what you see here is that the ALMA component, or the dust component of shown in red, tends to be more compact compared to the stellar component that's traced by the 1.6 micron observations with HST. And we find the overall trend that the stellar disk, or the stellar extent of the galaxies, tend to be more extended compared to the dust, and this tends to be systematic, and we believe that this is suggestive of the morphological transformation of the galaxies that are building their bulbs, because more confined dust in the center means that these galaxies are forming stars in the center, and therefore they can build on their bulbs. At the same time, bringing together the stellar component and the dust emission of a galaxy is not always straightforward, as we have increasing evidence that the two emissions do not coincide. They're not specially, we find special offsets between the dust emission that you see here in the contours from ALMA and the stellar emission from HST. And this is something that brings us to question the energy balance codes that we have been using in order to derive the fundamental properties of the galaxies. Of course, all this is going to be it's going to be benefited, and we're looking forward to a new era thanks to JWST that is going to characterize the stellar distribution and the stellar emission of galaxies out to redshift 11. And one of these projects is the Cosmos Web that will follow up the part of the Cosmos field, 0.6 square degrees of the Cosmos field, one of the most important cosmological fields, with NIRCam and MIRI, aiming to detect galaxies out to redshift 11, as I said before, characterize the masses and the star formation history, the morphologies and the sizes, and also try to establish a more robust halo to stellar mass relation. JWST will, of course, open a new window into spectroscopy at high redshift by targeting nebular emission lines. And as an example, this is a program by our PhD student, John Weaver, who was awarded time to follow up spectroscopically 5 UV luminous candidates at redshift between redshift 9 and 10. You can see here the spectral energy distribution and the probability distribution of their redshifts, along with some simulated spectra and the lines that we aim to detect, and all that to, of course, to quantify the bright end of the luminosity function and discuss the probability of the power lovers sector function, the AGN activity, and probably detect Lyman alpha emission. Just to say that the current record of the most distant galaxy in the universe is at redshift 11.1, while it's not formally spectroscopically confirmed, is what we call it's a combination between slit spectroscopy and photometry that has given us this redshift. So while we're pretty sure that this source that you see here is indeed at redshift 11.1, we are waiting for JWST to fully confirm it. Now, on top of JWST, of course, we're following up these sources with ALMA in order to detect the first dust and the first metals in the universe, as it's done by other groups. So you see here a collection of dust and of dust emission and emission line from oxygen 3 and C+ and other atomic lines in the far infrared out to redshift 9, and it seems that indeed there is dust and metals in the universe as soon as 5 gigayears after the Big Bang, and not only that, but the dust masses that we derive for these systems that you see here with circles. They cannot be accounted for by the traditional dust production mechanism, which is the AGB and the supernovae. But on top of that, we need to introduce a mechanism of rapid dust growth in order to accommodate these dust mass measurements so early in the cosmic evolution. Very soon we will move from this scarcity of post-stamping of collecting post-stamps of high redshift galaxies, of dust emission of high redshift galaxies, into fully characterizing the bulk of dust emission at high redshift, and also try to understand how the dust is catalyzing the star formation rate into the cosmic dawn. These observations will also help us put constraints into the evolution of the star formation rate density of the universe, that you see here on the left, and in the gas density of the universe that, as you can see, beyond redshift 4 is still largely unconstrained, with several groups advocating different evolutionary scenarios, and answer questions like about the rapid heavy element enrichment in the universe, and about the star formation efficiency in the universe in the beginning of during the kickoff of galaxy evolution, from formation to growth. Of course, in this regard, NGVLA in the next decade, and SKA will be also instrumental, because they will directly detect not only molecular hydrogen, but also atomic hydrogen, which is a key player into the physics of the galaxies. And here in this cartoon, or in this sketch, you see how the different gas traces and star formation traces, and how the different lines parade in front of the JWST, ALMA, and JVLA and VLA bands, and will help us to fully characterize the properties of the galaxies up to the highest redshift. So these, to me, are very particularly important for me, or interesting for me, is this H2 line, which is in the which is at rest frame mid-infrared, that is at very high redshift, is shifted into the ALMA bands. And by having high redshift candidates, or confirmed high redshift galaxies with JWST, we will be able to follow that up with ALMA. Moving now to the other end of galaxy evolution, which is the galactic death of quenching. As I have said before, it's still unclear what kills the galaxy, and more importantly, what keeps the galaxies dead, why the galaxies stop forming stars. While we still do not know what the answer to that question is, we know that the key ingredient that dictates the fate of the galaxies is the gas. So the several competing scenarios is that the galaxies do not accrete anymore gas, and therefore they run out of gas. So it's called cosmological starvation. This has to do with the growth of the dark matter halos. It could be that once the gas enters into the dark matter halo, it cannot cool sufficiently in order to enter into the galaxy and form stars through several mechanisms like viral shock heating, AGN feedback, and gravitational heating. Or it could be that these galaxies do retain some gas, but for some reason they cannot convert it into stars. You can think about it as your car that is not moving either because it ran out of fuel, or because it has fuel, but something happened to its engine, and therefore it cannot it cannot move. There are other scenarios about what might kill the galaxies, but as I said, we need to target the gas and measure the amount of gas in these systems in order to get a clear picture. However, this is extremely hard because measuring something that it's not in abundance or something that it's not there, it's a difficult task. And for that, we have to rely on gravitational lensing, which is helping us amplify the signal for the gas tracers, or use stacking. And using these techniques, we do find that the gas fraction of quiescent galaxies, of dead galaxies that you see here, are systematically lower compared to that of star-forming galaxies. But at the same time, we see that the gas fraction of dead galaxies in the early universe are about 10 times larger compared to that of the dead galaxies in the local universe. And so the obvious question that comes to mind is, if these systems do have some gas leftovers, then why don't they use it in order to make more stars? Why are they quiescent if there is still some gas in them? And we believe that the answer is here in the radio excess. We believe that this spectral energy distribution shows that there is a radio excess in these systems, possibly suggesting that there is some AGN feedback that keeps that prevents the gas from cooling and making new stars. And finally, and to make things even more interesting, we keep finding dead galaxies at ever increasing redshift, with the current record being at redshift 4, that corresponds to the first billion year of the existence of our universe, or if you wish, 12 billion years back in the past. So we have massive compact dead beasts that are already in place by redshift 4, something that is in tension with our cosmological simulations that cannot account for these systems. And obviously, it begs the questions of what the progenitors of these systems are, and where are they? And in the overall picture, we believe that at redshift 4 we have some we have galaxies going through a dusty starburst phase. Then it goes through a quasar phase, leaving a compact quiescent galaxy left over, and then it evolves to the local ellipticals. However, the detection of quiescent galaxies, of dead galaxies already redshift 4, rewinds the clock a couple of billion years, and it confines this evolution, this galaxy evolution, into the first 1 to 2 billion years in our universe, something that is quite challenging and interesting. And indeed, we have been finding, we just found some red QSOs at redshift 7.2 that we believe that are the progenitors of these dusty of these passive galaxies by redshift 4. I will not go into details about that because I'm already out of time. I will just say that in order to study these massive systems, these systems are quite rare in the universe, and by follow-up observations are not the most efficient way of detecting them. But we need large-scale observations. We need telescopes that cover a large parts of the sky, and of course, Euclid and LSST or Vera Rubin. This is the bread and butter for these systems. That with one pointing, they will be able to cover a lot of area in the sky and identify these early beasts in the universe. And of course, the ELT on the other extreme will provide unprecedented spatial and spectral resolution, much higher to that of JWST. And I finish by saying that apart from a multi-wavelength approach, we also need a multi-scale approach, because This with JWST and ALMA, we are of course detecting individual galaxies, but we also need intensity mapping in order to get the full the full amount of baryons within the group of galaxies that lie below the detection limit of these pencil beam surveys, and of course 21 centimeter observations to provide the tomography of the universe, giving us the amount of H1 that resides outside the ionized bubbles outside the galaxies. And when you bring all these things together, you will be able to fill these remaining parts in the evolutionary trend of the cosmic mass density, may that be stars, hydrogen, molecular hydrogen, atomic hydrogen, and whatnot. So I think that I have convinced you that we are entering in a new era of galaxy evolution, where we will be able to address some of the most fundamental questions into understanding how galaxies form, how galaxies grow, and how galaxies eventually die. And the way forward will be by bringing together multi-wavelength observations with the best telescopes that are becoming available. And that's it for me. Thank you.
Thank you very much, Giorgio, for this exciting journey in the life of a galaxy. So now time for questions, comments. So please go ahead, just unmute yourself and or raise your hand and discuss with Giorgos. So indeed, there is a question in the chat. Thank you from KM. Thank you for the great talk. A brief question. One would expect galaxies on the star formation main sequence to be mostly isolated system. Is this indeed the case? Apologies if it is already asked. Answer, I missed the start of the talk. And then we have Dimos. The clustered galaxies, the clustering, I mean, group galaxies is thought to be sites of accelerated evolution. So you would expect that in clusters you have a large fraction of quiescent galaxies, of dead galaxies that of course do not fall on the main sequence. And this is true in the local universe. And indeed, the massive systems and the systems that are
okay, may I go in? What's the situation?
Yes, please go ahead.
Yes, okay. That was a large synoptic talk. I enjoy very much because it gave a perspective, a global perspective, which I have not gotten. I don't work in the field, and therefore I don't know all the details. So that was a very interesting synopsis for me, replete with information, which of course goes beyond my understanding. I have several questions. I don't want to ask all of them. I'll ask one of them. Can I give somebody else a chance to discuss other things? So we have now the standard galaxies and the star-forming galaxies because the star-forming because of the colliding galaxies. Is that the reason? Before I'll let you answer, let me continue my syllogism here.
Yeah.
If you collide two galaxies, then basically the relative velocities of the order of 200 to 300 kilometers per second, all the gas that collides in there, and therefore you'd be a very hot gas instead of, and if you have very hot gas, it would be very hard to form stars. I mean, I'm surprised that the colliding galaxies are the ones that have high star formation rates.
The answer here is that based on simulations, what we see is that due to the merging, the galaxies, remember that in order to make stars, you don't just need cool gas, you also need to compress the gas. So the general idea in the simulations is that when two galaxies collide, the gravitational torque compresses the gas and makes it form stars more efficiently. But other than that, I completely agree with you. I think that this is still an open question that I don't think that has been adequately addressed by simulations. But indeed, we do find in the local universe that the galaxies that exhibit the highest star formation rates are indeed those that have disturbed morphologies and those that they seem to be undergoing a major merger.
Well, I mean, as far as simulations are concerned, let me just turn on my camera here.
Yeah.
As far as simulations are concerned, I've seen a number of those, and the resolution is not, of course, that will permit you to look at star formation. So people resort to what they call subgrid physics. Subgrid physics, basically, you can do anything you want because you want to eventually have something that your simulation has to simulate, and you arrange your subgrid physics to get what you want. That's my, well, I mean, it's a little cynical interpretation of that. Those are difficult simulations, there's no question about it. But from somebody who looks from afar, then it appears to me that there are lots of gaming going on at this point. But yes, I mean, I sort of, you seem to agree with me that if you have gas at 10 keV per particle, then that would be harder to make. But the observations indicate, and indeed, that the colliding galaxies or disturbed galaxies, if you like, they make more star formation. That's fine. So those are now eventually become the ellipticals.
That's the idea. Yes. Well, if you, because
the depletion of gas is so fast, it's faster by a factor of 10. So therefore, within a reasonably short time scale, the star formation ceases. They eat up all the gas. They make stars. The stars become old, and that's it.
Yeah. You are asking excellent questions that.
Yeah, I like this diagram that you had with the green dots. I thought that was very.
That's what I'm trying to get to. So, sorry, I can do that from here, I think. No.
Well, take your time. I don't know.
May I make a comment?
Yeah.
Yeah, go ahead, Vasily.
Dimo, Giorgio, it's an excellent talk indeed. Very Polish. Just first of all, I don't quite agree with the comment that Dimos made regarding the cooling of the gas, right? The fact that you have galaxies which are interacting with velocities typically in the order of 200 or 300 kilometers per second doesn't necessarily mean that the gas cannot cool, right? Because the gas is dissipative, so it can actually, we know that it loses angular momentum efficiently, right? And it will go into the center, and it will become, it will not behave ballistically. So ascribing sort of like average kinetic energy per particle on giant molecular clouds, which will interact with each other, right, may not be an accurate observation, I think.
To collide in molecular clouds, they will not remain molecular. That's the point. You collide them
right,
with
but you have
200 kilometers a second, they'll start emitting X-rays.
Yeah, but you also have dissipative atomic gas, right?
The simulations by Mijos and
this was done way back, you know,
yes.
In '96, Mijos and Herdquist, for example, when I was finishing my PhD, and then more sophisticated simulations, which actually do have proper physics that Phil Hopkins is doing at Caltech, for example. I think they address this issue. They address this issue convincingly, I think.
All right.
So there are no real difficulties in subgrid physics when you deal with pairs of galaxies, for example, in the nearby universe, where you also have data in atomic gas, molecular gas, and everything, right? Clearly, when you have, you know, cosmological simulations and how we go from a large scale to smaller scale, and how feedback works, if you want to create statistical samples, then this may be more challenging, right? This was just a comment.
In conclusion,
yeah.
The issue I raised has been resolved, so it's that's what
I would say yes for galaxy pairs. My feeling, I don't know what George thinks, but
I'm not 100% sure, Vasily, because we see mergers on the main sequence that they do not have elevated star formation, and we see galaxies that tend to look isolated. So the overall picture.
I mean, the fact that galaxies interact does not necessarily mean that the star formation needs to go down extensively, right? Even the comment that main sequence galaxies need to be isolated doesn't mean that they need to be isolated, right? I mean, you have the Milky Way and the Magellanic clouds, which have been interacting, right? But none of the two has elevated star formation rate, right? So
yeah, a major merger, but
the burst of star formation also is very short-lived, right? This is one of the premises of the main sequence. You can have pairs of galaxies that had a burst of star formation at some period, but now they are quiescent because you have massive star formation and winds which push the gas from the nuclear regions out. So you go down to a star formation rate of 4 or 5 solar masses per year, and you have 10 to the 11 systems. So
and that brings me to the other point that you can go down to quiescence. We still do not know. There are two avenues. The one is that you very fast and very efficiently get depleted of gas, and you shoot down from the starburst phase. But there are also advocates of the slow quenching, that it's just that the galaxy falls into quiescence without becoming a starburst first. So, yeah.
Let me lower my hand and give somebody else a chance to say anything, something.
If there is no other question, may I ask one more, Giorgio?
Yeah, of course. I mean,
the first one was you mentioned about the difficulties in observing the gas inflow, right? To provide the actual fuel, right?
Yes.
And you alluded in the end, is it possible that SKA will actually be able to do that?
Maybe yes. Well, the SKA is going to detect H1. From my understanding, from my limited understanding of the inflows, the problem is that it can happen in. So it's a 3D configuration that it's on a 2D projection. So you do not actually know, and you do not know where the inflow is coming from. So you can have a diluted signal just because of the configuration of the inflowing gas. But yes, SKA is supposed to be one of the main instruments that will measure this inflow into the system from H1, I guess.
Okay. And the second one, you had shown, I think it was just a couple of this very close to your slide, this halo mass, the preliminary result, right, that you had shown, yeah, that slide, right? I was a bit wondering here, since the most massive halos are formed first, right? When one makes this type of correlation, can you do it for the same snapshot in time? You see what I mean? So
so you say that these halos here are more evolved than
correct
than these ones? Yes. Yeah.
Well, if I see these 4 boxes that you average out, I suppose the boxes are the averages, right?
Yeah.
That's, to me, looks more like a straight line than the curved line that it's shown there. But
yes,
anyway.
There is a lack of sources here, indeed.
Yes, well, whichever way you. Well, anyway, there's somebody else who wants to ask a question.
Sorry about that. Yeah. Thank you.
Kostas.
Hello. First of all, thank you very much for the very interesting review, Professor. So my question is probably naive because I'm not working on high redshift universe. So I want to drag you a little bit back to the beginning of your talk. In the beginning of your talk, you showed you said about the dawn of the galaxies in the universe, that the peak was about the redshift 2. But then a little bit afterwards, you saw the main sequence of as a function of redshift. And this showed that, if I remember well, that the specific star formation was higher as we moved to even higher redshifts than redshift 2. So I don't understand if there is a discrepancy there. Is there another reason that shouldn't be in this in that way? This line shouldn't be higher for redshift 2 compared to the other lines, or is it something that I don't get here?
No, that's a good catch. Well, actually, you see how the increase in the specific star formation rate is the jump between the redshift is getting progressively smaller.
Shorter,
actually,
yeah.
and this is actually what is telling us that we're reaching the peak of the star formation activity. And actually, what you describe is a question that it's only very recently answered, because the simulations predict a much flatter evolution of the specific star formation rate compared to the one that we observe, that it keeps sorry, it's the other way around. It's increasing, and we are seeing a plateau. So the difference here is that this is what you see here is per galaxy, per individual galaxy, and here is averaging the star formation activity of the universe. So to put it simply, if you don't have a lot of massive galaxies to produce a lot of star formation rate, then you see what I mean. It's a matter of number density of massive galaxies that contribute the most into the star formation activity.
Okay, I see. All right. Okay, thank you very much.
Okay, other questions, comments to Georgios? I don't see.
I have several questions, but I want to give other people a chance to ask before I monopolize yours.
Okay.
So, well, anyway, so the interesting point, as far as I'm concerned, is that the diagram you just showed, this is basically scaling laws that kind of, things that don't happen randomly, haphazardly. You show this diagram now. Can you put it back up? The one you just showed, the star formation. Well, even
this one.
Yeah, this one. Yes. I mean, I assume that we don't. Do we know of any galaxies with mass of 10 to the 11 solar masses at 0.5?
No.
No. But anyway, the point is that there's a sequence that follows time, right? So you start with a red line, and as time goes on, you do have, of course, you don't go that high in mass, but within the masses you can tell. That's my understanding of this diagram. You have sequences of star formation associated with galaxies of a given mass, and eventually will come to z equals 0, which is the thick line that you have, the gray line. Do I understand?
If I may add, a galaxy moves like that. Whoop. You see?
A galaxy.
A galaxy. If you think of a galaxy at redshift 5 with a mass 10 to the 10,
yes,
it will grow like that. It will.
I see. So now it has mass 10 to the 11 because of accretion. 10
to the 11, but it also goes down in its star formation rate.
Star formation, yes, that's fine.
Yeah, they do not evolve that way. They evolve like that.
The whole line doesn't evolve lower. It just basically evolves diagonally, and eventually that's what we see at z equals 0. But we see at 0.1. I assume you must see massive galaxies at z equals 1.
Yeah, of course. Among the fraction of dead galaxies, of passive galaxies, increases dramatically as you go to higher stellar masses. So the majority of mass
ellipticals.
Yeah. Well, yes.
I call them ellipticals.
Yes.
That's because maybe I'm too old, much older than you are, and we used to call them ellipticals. Okay, well, there's another question there other than mine. I have more, but Sotiria should ask a question first.
Hi, Georgios. Thank you very much for the very nice talk. So my question is more about the very high redshift stuff you showed. Is there really room to assume there's going to be some rejuvenation in the galaxy between the properties that you're measuring at the very high redshifts and what we observe for very massive passive galaxies at low redshifts? right? Or put it another way, if you would put those very high redshift stuff on a scaling relation, let's say on an M sigma relation, where would they fall?
Yeah, the rejuvenation, again, there are several groups that are advocating that, that a dead galaxy, for whatever reason, could rejuvenate. But I think that the general consensus is that this is not a favorable scenario based on with spectroscopy. You can get information about the star formation history of these systems, and therefore time the last star forming event and see whether there is a rejuvenation or not. And I think that so far that most of the systems do not appear to have been rejuvenated. I don't know if I fully answered your question. Again,
yeah, so these would be really the progenitors of what we find in the centers of very massive clusters these days.
Yes. The question here is, how did they have the time to form so early in the universe? How can you have because Demosthenes asked about 10 to the 11 galaxies. This is a 10 to the 11 galaxy at redshift 4 already, and not only it's a redshift 4, but it's dead.
So that's a large, an elliptical at Z4, basically?
Yes.
Shall we be able to see them with the JWST any better than that? No?
Well, yes. Well, that's the whole, the whole thing is that based on HST and Spitzer and ground-based spectroscopy, the ground-based photometry, we cannot select dead galaxies based on the spectral features. We cannot select galaxies at
high redshift.
Higher, yes, because the Balmer the break moves into the mid-infrared. Right. This is what JWST is going to do. Hopefully, we're going to detect the massive system. But on the other hand, the difficult thing here is that JWST is not a survey instrument. Because it's slewing capability is very slow. So from moving from the one part of the sky to the other, it takes ages. It's more of a source by source instrument rather than a survey instrument. For that, we're going to have Euclid and LSST, as I said.
Or on Roman, I suppose, too, right?
Yeah.
So one final question from me before I get my hand down and shut up. So all these objects are virially supported? They're all virial?
We need to know the kinematics in order to...
So we don't know, at high redshift, we don't know basically. Because we know locally they're virial. We measure it.
You mean the dark matter?
We don't see the dark matter, we see the stars.
Yes,
we see the stars, and it turns out the virial theorem has basically velocity, relates velocity with mass and radius. And if all those three were free to vary, be random, then if you plot velocity versus radius, you will fill the entire diagram, and it doesn't. Or if you plot mass versus velocity, it will fill the entire diagram. It doesn't. It fills a line, and that's called the Tully-Fisher relation, or the Faber-Jackson relation. And interestingly enough, the same relations are also followed by the spheroids, which are the centers of galaxies. But and I don't understand all that, but maybe you have an idea of what does this relation come about?
Well, we think that we're doing I think that we're doing the opposite. We're doing the kinematics in order to, assuming that they're virialized, in order to infer their dynamical mass.
Yes. Okay.
So we assume that they're virialized, and indeed we do find things at redshift 2, 3, 4, or whatever, where we see clear rotation. We see clear dynamical rotation. We measure the velocity and the velocity rotation, and we invoke the virial theorem in order to get the dynamical mass of the systems.
And it is, of course, it's more than the observed mass, I assume, because that's true
That's
true in local systems.
Yes. Again, you're touching a soft nerve here, because for the high redshift elliptical galaxies, just to speak your language, the elliptical galaxies, we do find that the stellar mass appears to be the same, equal, or even sometimes higher than the one inferred from the dynamical masses, which obviously means that there is something is off. And what we believe that could be off is the assumption of the initial mass function that is assumed for the stellar mass of the systems. And if you change the initial mass function, then you are changing the mass budget of the stellar mass budget of these systems.
Of course, you have to assume something about the distance, and the distance depends on the Hubble constant. And I don't know.
We know the distance because we have okay.
The Hubble constant is apparently uncertain by 10%, whatever it is, from 67 to 73. So, all right. Thank you very much. I will stop here. I'm not going to ask any more questions.
I think, Dimo, you should invite Georgios to come to Goddard and give a talk there.
Yes, that's true.
Now that we can come to the US even as tourists.
Absolutely.
It's open. I'm sending my PhD student to Caltech next week.
Okay, other questions to Georgios? I think he's got enough. So let's thank again Georgios for the very nice talk.
Thank you.
So thank you also everybody for joining in. Have a nice afternoon.
Bye.
Bye-bye.